Hello, my name is Pavel Reutberg and the topic of today's webinar is AI at the Edge, private low-power monitoring for your operations. First of all, what is the webinar actually about? The focus will be using CAD geometry for object pose estimation, as you can see in the video on the left-hand side. This means we assume some kind of industrial or production context where CAD files are actually available. Using CAD files means that typically no real color is available, and in this context we even are not using any real data at all. We are only using synthetic data, as you can see on the right hand side of this slide. This means the neural network that is performing the task on the left hand side is only using geometric shapes and no color information about the parts. Before I give you the details of how we arrived here, let me lose a few words about myself. I'm a senior researcher and project leader at the Fraunhofer IGD, and my research interests are computer vision and machine learning, and specifically 6D object pose estimation. As the project leader, I participated in the EU project Distributed AI at the Edge and the Fraunhofer project Sensor Edge Cloud. In case this is the first time you are hearing about the Fraunhofer Society, Fraunhofer Society is Europe's largest applied research organization. It consists of 76 institutes and research units across Germany, and its goal is bridging research discovery in industrial applications, as hopefully you will see as part of this webinar. With this, let's move on. First, the outline for the remaining 15 minutes or so of this webinar is as follows. I want to motivate why it is desirable to move beyond cloud dependency towards edge AI. Then I want to cover some fundamentals of machine learning training as a prerequisite for the rest of the talk. Specifically, I want to go into detail what constitutes good training data and how to use your CAD files for training. Finally, I want to conclude the webinar with moving or giving you an outlook what might come beyond frame-based vision and how to do synthetic training on this new neuromorphic modality. Okay, with this, let's motivate why one should look beyond cloud dependency. First of all, the big advantage why you are using the cloud maybe in the first place is the scalability. However, scaling up your cloud deployment means you increase your cost and also the power consumption of your deployment. Additionally, it is difficult to reach a real-time operation in the cloud scenario because the load of your cloud node is out of your control, and so is the network. And obviously, offline operation is not possible because you always need an internet connection towards the cloud. Speaking of the cloud, it is actually looking somehow like the image on the left-hand side. It shows an NVIDIA DGX unit, which is typically used for machine learning deployment in the cloud. So in a nutshell, using the cloud means you are renting someone else's computer, and it comes with all the difficulties of doing this. So the first or main difficulty is doing intellectual property protection. And for this, you typically need some kind of end-to-end encryption to transfer your data to the cloud. But even if you do end-to-end encryption, you still need to decrypt your data to actually do the computation on them. So this opens your data up to breach risk. So if somebody enters the data center and your data is currently being computed on, they can just access it by accessing the machine. Then there is the availability. For instance, Office 365 was only available for 361 days in 2024. So in case you happened to have something important planned for the 4 days of downtime, you were out of luck. So in this webinar, we want to focus on the edge device or target the edge device, which you see on the right-hand side. It is an NVIDIA Jetson Orin device with 8 GB of memory and with a peak power consumption of 25 watts. This low power consumption makes it or allows you to integrate this device, for instance, in the car, because the heat is also very limited. And because we have this specific device, we can do hardware-aware deployment where we optimize the neural network using this automated TensorRT framework for the specific device. Of course, using this embedded device limits the machine learning models that you can use. For instance, you cannot deploy a large 30 gigabyte large language model on this 8 gigabyte device. But before we talk about the specific machine learning models, let's turn to how do we represent our task that the machine learning model is supposed to solve for us. Typically, this starts with some manual labeling, as you can see on the left-hand side. This is probably familiar to you. This is a labeling environment where you place the bounding boxes that are supposed to be predicted by the neural network in the end. This is a manual process, and it's very time consuming because you need to place a lot of keyframes between which the bounding box position and size is interpolating. And this is not very precise, but typically accurate enough to say how many runners are in the image and who of the runners is the first place currently. The same can be done for 3D, as you can see on the right hand side, but it is even more time consuming, and it also requires precise camera tracking like a SLAM system, because if your camera tracking is imprecise, your data will be imprecise too. And it's more time consuming because you need to look at the bounding box from different camera angles to see whether you placed it correctly. And still you cannot give any accuracy guarantees because you cannot promise whether your bounding box is precise to millimeters or centimeters or whatever. Before I want to give you a better solution for 3D data annotation, let's talk about another problem of machine learning data generation, and this problem is dataset bias. Because our expectation of training is that we give the neural network some training examples, and the neural network will then generalize to our testing environment. But unfortunately, this does not work without further considerations. Let's take a look at the quote I have on top on the slide, which is done by the inventor of the YOLO network, which is very famous nowadays. And it says, with great power comes great overfitting, which means that the more powerful your machine learning model is, the more likely it will just remember parts or most of the training data and not generalize beyond this. As an example for this, I want to show you these images on the left-hand side, which show the car category from two different data sets. And if you were to train on one of the data set and test on the other one, it will probably not work. For instance, if you train on the sedan data set on the top, it will not detect the sports cars because they are very different and have different shapes and have different orientations, while in the data set they are all aligned to the left. So this one is called selection bias, which is one part of the dataset bias, and the selection bias is that we only have sports cars or only have sedans in one of the data sets. Also, we have another bias in both the data sets, which is the negativity bias, and we have no images without cars in this case. So our machine learning model might just detect the road and not the cars, and will say, okay, this is the most common thing beyond between all these images. And the same problem is even stronger when it comes to 3D pose estimations, as I want to show you on the right-hand side, where you see a point cloud of a street scene, and we have camera trajectories of the camera moving through the scene in these colors. So in red we have the training trajectory, and in green we have the testing trajectory, and then we have three different algorithms. We have two neural network based ones and one classical one in Azure. And as you can see, the neural network algorithms in blue and pink stick to the training trajectory and do not generalize to the testing trajectory, because all they see are the training images. What I want to motivate with this is that the neural networks are not learning through 3D understanding, but are much closer to some search or image retrieval algorithms, because they don't employ this scene understanding, which is encoded via PNP in the classical method. So all in all, this means that we cannot expect our neural network to generalize outside of training data, be it the camera specific car or be it the camera pose. We can expect it to interpolate between the training data, but we cannot expect it to extrapolate. And both of the issues I show you on this slide also apply to manual labeling, because even if you could do perfect labeling for your recorded data, the data recording itself is a problem. Typically, you go outside and it might be raining, so you don't pay attention how you move your camera through the street or which cars you are filming. But this heavily influences whether your neural network will be able to generalize or not. So instead of doing this, I want to propose a different solution, which is synthetic data generation. And this means we are using our CD model, which is shown on the left-hand side, and then we feed it into a 3D rendering pipeline to generate images like you see on the bottom. And this means, because we are using synthetic rendering, we know for every pixel whether this is an object or whether this is a background and which object it is. So we get basically the labeling for free, and we get it pixel precise. Also, this enables us to do something which is called domain randomization. And in a nutshell, it means we can randomize things that we expect to vary. For instance, we don't know what the background will be in the final scenario, so we can use random backgrounds. Also, we don't know the true color of the CAD file, so we can use random colors as done in this example. And most importantly, we can use realistic viewpoint positions. So we can ensure that all possible viewpoints are actually covered in our training data. And all this together forces our neural network towards stable features. And as I said on the first slide, in this case, this is the geometric shape and not the actual color of the object. However, we need to pay attention here not to create a new dataset bias, which is called the reality gap. This is why we feed the CAD file through a physically based rendering pipeline, which means that the lighting and shadowing is very realistic, and the images that we are generating are close enough to reality, so the neural network will also work on real data. And as I've shown you in the beginning, we verified this, and it indeed is close enough to work on the video. And you are not only benefiting by this when using pose estimation, but you can also use the pixel perfect labels for classical 2D annotation, as you can see on the right-hand side, where we just draw 2D bounding boxes around the objects that we are interested in. And with this, I want to come to the final part of this webinar, namely moving beyond frame-based vision. So what I want to suggest will come after frame-based vision is event-based or neuromorphic vision. And I want to explain what this is on this slide. So in RGB or frame-based vision, like shown in the picture on top, we have some discrete timestamps at which we capture the whole sensor content. And in contrast, in event-based vision, we have pixels that are able to send data independently. You might think of them of having, instead of having one global shutter for a frame, you have a shutter for each pixel individually. And as soon as the brightness of the pixel changes from bright to dark or dark to bright, the pixel sends an event that this thing happened. And this means that only motion is recorded and that only interesting parts of the frame needs to be transmitted. Because only a few pixels typically change in the frame, the data that needs to be transmitted is much less, and it can be sent much more rapidly. And this means we have a quasi-continuous time domain. To make all of this a little bit less abstract, let's take a look at a real-world example. Here we have a recording of a moving motor. On the left-hand side, we have the RGB stream, and on the right-hand side, we have the event stream. So at first glance, you might say that the event stream is very similar, and we still have this motion blur. But as you can see, if you move with the mouse cursor about on top of the moving parts, we can actually um, measure the frequency at which the pixels change. So the motion blur is only happening because we did not slow down the recording. We still can measure all the pixel changes, and this allows us to measure the frequency with which the motor itself is vibrating, or the frequency with which the disk is rotating, which is above more than 200 hertz, which means that the event stream is equivalent to more than 200 frames per second, which I would say is quite impressive, given that we are still only using passive frame-based or optical sensing of the motor. A different advantage of event-based vision is its higher dynamic range, because each part of the frame can have its different, its own shutter. We are not affected by being blinded by the street lamps like the frame-based vision on the left-hand side. So we can detect the pedestrians much more reliable, as you can see on the right-hand side of the frame. Typically, the event-based sensor has double the dynamic range than an RGB sensor. And the final advantage of event representation is the low power consumption. Because we are only transmitting much less data than an RGB frame, it also takes much less energy, which boils down to around 1/10 of the power required compared to an RGB sensor. On this slide, you see an experiment conducted by a different group, not at Fraunhofer, where the goal was to monitor the penguins at the South Pole. Because the penguins have no power line, the whole system had to be self-contained and battery-powered. And in order to reach the high enough frequency to actually record the motion of the penguins, the RGB camera would have drained the battery very fast. So instead, the RGB frequency was around 1 every 5 seconds, and the actual motion was recorded with the event camera. And as you can see in the event stream, we capture the rain that is falling and the motion of the penguins. However, this is also the largest disadvantage of a event-based sensor. And to highlight it, I want to use this scene from Jurassic Park, where it says that if you don't move, the T-Rex cannot see you. And this is the main disadvantage. If there's no motion, the event camera is basically blind. But actually, the T-Rex thing is a misconception, and the T-Rex had very good vision because they had very big eyes. So to be more realistic, think of a frog instead, because they actually have this event-based low-level vision where the eyes only send information if there is motion. But anyways, let's turn back to our synthetic data generation and the application of this fact on them. So when previously we could render individual frames to train on, now we need to generate motion to get realistic events out of it. So for each sequence on the left-hand side, we get one single event frame on the right-hand side. So we collect 34 frames and then feed them into event simulator to get the simulated frames. And as we done with the RGB frames, synthetic RGB frames, we also did an experiment whether the event frames are realistic enough. And you can see the results on the left-hand side, where we tested it with a real car, but unfortunately it was only a toy car. But as you can see, it was close enough to be detected. Also, if you want to evaluate any advantages of the event camera compared to RGB frames, we created a data set where we have synchronized event frames and RGB frames, and also pose annotations where you can test whether the advantages are worth it for you. And the title is on the bottom in case you want to search for the data set. With this, I want to give you some more examples of synthetic data generations and the applications of it. On the left-hand side, you see a drone detection where we again only had a synthetic CAD file of the model of the drone, and we are able to detect the drone, but also where it is heading. so we can predict where it will move next. Currently, we are moving towards event detection of the drone because it's a much more fitting task because we have a stationary camera and only the drone is moving. On the right hand side, you might you see something where you not immediately think of when thinking about CAD files, where we have strawberry detection and pose estimation, which is very useful for automated strawberry harvesting. And here we had some procedural generation of strawberries to cover the wide variety of different strawberry shapes. And this allowed us to detect all the strawberries in the real image on the right hand side. And with this, I want to conclude this webinar and thank you for your attention. Here you see a small recap of what we talked about today. We talked about synthetic data generation. We talked about pose estimation and how to catch the dataset bias with synthetic data generation. And finally, we talked about the event cameras or neuromorphic cameras and pose estimation using synthetic data on them, like you see on the right-hand side. Okay, so thanks for your attention, and I'm looking forward to your questions.